Welcome back, everybody, and welcome to this new week. And the topics this week, when we look at the weekly schedules, is actually to discuss a little bit more about second quantizations. And we're going to repeat some of the things which we discussed last week. We are going to look at second quantization and also something which we are going to call a diagrammatic representation, but we're only going to scratch the surface of that. And then there is a very important theorem, which is called Wick's theorem, which is the one which gives us a much more compact way of calculating expectation values. So I wanted to give you a quick reminder of what we did last week. And then we are going to look at examples and repeat some of the things which we did last week. And when we've done that, we are going to dive into how we represent operators in second quantization. And in order to do that, we need to remind ourselves of some kind of hidden element in linear algebra, which is called a spectral representation of operators. I don't know if you've seen that, but that is a technicality which we need when we are going to derive the equations for the operators in second quantization. I guess the spectral decomposition is something which may ring a bell, but it's one of these kind of things which sometimes it just pops up in textbooks and you're supposed to remember it. So I just wanted to give you a quick reminder of that. And then Wick's theorem is something which we will prove tomorrow. And Wick's theorem, if you go into many textbooks, unfortunately, it's just listed as a theorem. And it's actually useful to see how you get to that theorem. And that's a proof by induction. It's not very difficult, actually. The third exercise set, you can click on this link or just retrieve them from where you have the lecture notes and the GitHub address. So if we look at what we did last week, we looked at the commutation relations. So this is one of the commutation relations which we derived last week. We have the properties of these creation and annihilation operators. They are typically summarized for fermions, and this is the case we will deal with in most parts of the courses here, And this means that when this acts on this state 0, we get a state which is now filled up with a component with a particle in a state with a single particle quantum numbers alpha. And when we act with this operator on that specific state, so this is a way we're going to represent the determinant. This means that we would have a new determinant, which in the previous case contained n particles, and now it contains n plus 1. And what we have defined is a new way of writing the determinant in terms of this this creation and annihilation operators. We also have the annihilation operator, which is just the Hermitian conjugate of the other operator. And then we found these commutator algebras for fermions. So these are the fermion creation and annihilation operators. And these are the quantities which we will use throughout basically throughout this course here. So before we move on now, I just wanted to repeat some of these things on the whiteboard so we can slow down the pace a little bit and also go through examples so that you get a feeling for what these operators actually mean and how we are going to use them. And then, as I said, I'm going to give you a quick reminder about this spectral decomposition of an operator. And we are going to use that one to actually set up the expression, as you can see a little bit later here. We are going to set up the expression for a given operator in second quantization. Now, some of the things which you will see here are not the most exciting things. So I will use a mix of whiteboard and slides. Here, we are just going to operate on a given state with permutations and without. And then we are going to see how we can use this one to find a compact expression in second quantization. So I'm going to switch to the whiteboard. So let's do that. So the just as a reminder, with some kind of additional technicalities, which are can be useful if you want to have a kind of better understanding of what is going on. So if we now look at these operators which we have defined, so we have defined something which we called a vacuum state. And we developed that. This is actually a vector. So how to understand that one is by just looking at the single particle states which we have at our disposal, and think of these as specific slots. So we would have quantum numbers like alpha 1, alpha 2, and this goes all the way up to n. So uppercase letter n is actually the number of particles which we have. The lowercase letter is the total number of single particle states which we're dealing with. And you can think of every one of these as a box. And in each box, you can then put in one particle, or you can have 0 particles. So if you then continue, we have n plus 1, and this moves up to an alpha little n. In principle, this is equal to infinity when you have a basis like a harmonic oscillator, because you have an infinite set of orthonormal basis states for single particle. So this just moves on, etc., etc. So now what you could think of is, suppose you're looking at these slots here, you could now rephrase this one in terms of you having 0 particles in every slot. So just think of the open circle as 0, right? And a filled circle then is just a 1 particle in a given slot. So when I fill these slots, it means that it's a particle. When you have an open circle, it's just an empty state. So I would then characterize that state, which you have here, just emptiness. You would set that one, define that one as a vector, which is 0. So in principle, you could write this one as just a vector with 0, 0, 0, and zeros. So there's nothing here. So let me just take that one out. But this is now a vector in this space of states. And if we have now 2 particles, for instance, suppose now we fill alpha 1 and alpha 2, then we would have a new state. So let's now suppose we have this one. And this is alpha 1 and alpha 2 here. And then we have this infinity of states, which moves on like that. This is something which we would then write out as a creation operator alpha 1 and alpha 2 acting on this vacuum state. And now we are filling in states alpha 1 and alpha 2 here. So we would typically write this as an alpha 1 and alpha 2 here. Now, if we want to write this in, suppose now that we have only 2 states. So this is a simplified system. So we assume now that just for the sake of simplicity, that n is equal to 2. So just 2 states. And if we then look at one of the states, alpha 1, alpha 2, which we have here, in principle, this is just the tensor product of alpha 1 and alpha 2. And we could think of our orthogonal basis. In this specific case, alpha 1 could be equal to 1, 0, since we have these states. And that means that we would have a word which looks like this, 1, 0. And then when I look at alpha 2 here, that could be a state which is 0, 1. So we are assuming that these are orthogonal states to each other. And we would then encode this one as 0, 1. So this is the 1 particle state. And this is one type of coding which we could use. Now, what we have, however, is in principle an alpha 1, alpha 2 here, which is a tensor product, which means that what we get then when we perform the tensor product, so we would have 1 acting multiplied with 1, 0, and then we have 0, and then we have 0, 1. So these are just multiplied, so that gives us a vector of length 4. So we would have 0, 1, 0, 0. Now, just pay attention to the way you're coding things, because you can code things in a compact way or in a less compact way. So what you see first here would be a way to classify a single particle state in this domain. But this becomes a little bit unwieldy when you have many particles. So typically, the kind of representation you would use now would be not this way here of representing it, or this one, and not even this one, because this is something you could write out as a state which goes like 0, 1, 0, 0. But then it becomes a little bit more clumsy. The typical way we would write this one, this state which you see here, this one, would be something like alpha 1, alpha 2, and then you would simply have 1, 1. So there are many ways you can classify things, right? So you can specify 4 different states where you have all particles in, let's say in this case, we have particle 1 in slot alpha 1 and particle 2 in slot alpha 2. And the compact way by which we could represent that would just be by this word here. Alternatively, we can use this representation, but that requires often a little bit more space in memory. So we are just thinking about compact ways of representing a given state. And when I write a state like this 1, 1 here, that would now refer simply to this state here, but where we have only 2 single particle states. So if I have 4 single particle states, the kind of nomenclature we're going to use is now, so with the little n equal to 4, and the number of particles equal to 2 here, then we could have a situation where we now fill in these boxes. So alpha 1, alpha 2, alpha 3, alpha 4. And just keep in mind that each one of these now represents one possible orthonormal state, single particle states, which are orthonormal. So this situation here, with these ones empty, is something which we now could encode as a compact word, like 1, 1, 0, 0. So that would be a compact way of encoding this information. So where every slot now stands for us having either occupied or not occupied, bit 1 or bit 0. Alternatively, since now you have 4 single particle states, you could have used a representation like the one you have here, but then you would have to augment that one so that you have 2 more single particle states, which the system can be in. So in this specific case, we actually assume that you had only 2. If you have 4 such states, then you would probably need a vector of length 4. And when you're setting up the states here, you would actually have to put up a tensor product of these 4 single particle states. So your basis, which we write in such a compact way, which you see here, this is just written as a word. And if you have 4 states, you need, if you're dealing with integers, which these are, then you would just need 4 bits to represent that state. So these are compact representations which you can set up. And in principle, however, when you look at a state like this one, so this is obviously the tensor product again of 2 single particle states, alpha 2, alpha 1. But now we could keep the information which you have here, and set it up like that, or you could skip it to make it even more compact. So the way you label the states and number them depends on what is the most convenient way to represent a state in a computer. So when we have two single particle states, we are going to stay normally with a notation like this one, alpha 1 and alpha 2. But keep in mind that that actually means a tensor product between two single particle states. But we use this compact notation. And later, if you want to represent things as words in a computer, then you would have realizations like this one, but you could also have a realization like this one with two particles. You could have a 0, 0, 1, etc. So these would be all the possible ways you can distribute two particles in these 4 slots. So this is just a kind of technicality, but keep in mind that when we now define this vacuum state, it is actually a vector. So which in principle then means that if you were to represent the vacuum state here, it should be 0, 0, 0, 0. Okay? Does that help a little bit? Because the thing which can confuse people in the beginning is that when we now act with an operator like this on the vacuum state, then there is nothing to remove. So we define that as 0. And that is not a vector. That is just a scalar, a number. Okay? Any questions? Does that sound okay? So these are just definitions which sometimes can confuse us a little bit. Another thing which, since we now are taking away the spatial degrees of freedom, if we look at a state where we have quantum numbers the system can be in, and then some additional variables like the positions and the spins of the particles, this is normally written as this overlap between the spatial degrees of freedom and the other quantum numbers. So that is also a kind of compact notation which you will encounter. And remember now that when we deal with second quantization or the number representation, we are in a way not including anymore the spatial degrees of freedom because they will be incorporated in integrals. So we are going to leave them out and bring them back again when we are plugging in specific integrals in the equations. So you could think of you having tabulated specific integrals for, let's say, the Coulomb interaction, or it could be any other type of interactions, and also the one-body operators. Okay, and then the Slater determinant, which we would have when we fill in all the states, an SD, is normally defined then in this notation here as an alpha 1, alpha 2, all the way up to some alpha n. And sometimes we put an AS under it to remind ourselves that this is an anti-symmetrized quantity, but it's often common to skip it. So from the context now, when you see this, this is going to represent a Slater determinant. Also, let me remind you of the other calculational rules. If this acts on that state, that brings us back a 0, which is the vacuum state. So there are some calculations which we started with last week. So let's take a look at some of these calculations again. And we are going to introduce a more compact notation for some of these types of calculations. So one of the things which we introduced last week was what we called the number operator. And that is a sum over all the possible quantum numbers of the system. So this could go from alpha 1 up to some alpha n. And then it's an operator which looks like A alpha times A alpha dagger, A alpha. And this is a quantity which just computes the number of particles and gives that as the expectation value. So something which is useful to see with this operator is also that this operator, when we take and square it, so let me just bring up that one. So if I square this operator, we can easily show that this is equal to the operator itself. The other property with this operator here is that if we take a specific component, so let's just take one of these components and write this as an A dagger AI. If I then take the commutator between two of these components, the standard commutator, this is equal to 0, so they commute with each other. This is actually easy to see. You will get this as a kind of exercise next week. And then we have another important rule here, which we are going to use a little bit later in connection with other methods. This is given by ij of AI. And finally, so this is just the Kronecker delta, delta ij. And then finally, we have AI dagger with a number operator, which is equal to minus delta ij multiplied with AI. So one of the things which we did last week was to calculate the expectation value of that operator with a state which had two particles only. So these are relations which we will play around with next week in the exercises. So I want you just to show these equations here. So let's now take a look at where we were last week. So we had an example where we looked at the state alpha 1, alpha 2, which is A alpha 1, A alpha 2 here, with acting on the vacuum state. And we wanted to calculate the expectation value of that quantity for the number operator. But before we do that again, let's do a simpler case. And then we use that one to remind ourselves on how we're going to calculate the number operator as well. Now, the reason why I do this is that I'm going to introduce some notations which will be helpful when we come to Wick's theorem. So let's take as an intermediate step and just look at the norm of these two states here, alpha 1, alpha 2, in second quantization. And then after we've done these calculations, we are going to jump back to the number operator, which we looked at last week, and just remind ourselves of how we computed that one. Now, if we look at this one, this is simply going to be given by this compact expression, alpha 2, A alpha 1, and then alpha 1 here, and then alpha 2. So this is the kind of ordering which we have chosen. Now, the way we can do this in a very brute force way is to now move all the creation operator to the left and the annihilation operators to the right. Because when we have that, then this alpha 1 here will be acting on the vacuum state, and that will give us 0. So the whole procedure, which Wick generalized to Wick's theorem, is to rewrite such an quantity like the norm in this case, or an expectation value, or a transition probability in terms of what we are going to label as contractions, which are the Kronecker deltas between operators, creation and annihilation, and expectation values of operators where we have all the annihilation operators to the right, acting on 0. So what we are going to do now is just to repeat a little bit of this kind of brute force exercise we did last week, but now we apply it to a slightly simpler quantity. And then you will quickly see that when you add an operator to this, it's going to complicate life. And we are looking for something or a simpler recipe. So the straightforward brute force way is to use the anti-commutation relations. So what we would do then is that we would now first switch alpha 1, alpha 1. So this gives obviously alpha 1, alpha 1. So that's just 1. That's pretty obvious. And then I have an A alpha 1 dagger, A alpha 1. And then I have an A alpha 2 dagger of 0 here. So if I now take the second expression, which you see here, if we now just write this out, what we have is 0, and then we have an A alpha 2 dagger acting on 0. And this is multiplied with delta alpha 1, that Kronecker delta. And then I have a minus, and then I have my 0, A alpha 2, A alpha 1 dagger, A alpha 1, and then A alpha 2, like that. And if we look at the second term, this is something which we now can rewrite by looking at the commutator between these two operators. So if I do that, then I can rewrite this. So let's just do that. So we're going to have the first term. So it's okay if I switch page, okay? So we're going to have one term, which is 0, A alpha 2 here, A alpha 2 dagger, 0, delta alpha 1, alpha 1. And then I have minus. So if we pick up the first term, we're going to have a term here where we now are going to interchange alpha 1 and alpha 2. So we're going to have minus 0, A alpha 2, A alpha 1 dagger. And then I'm going to have delta alpha 1, alpha 2 minus. And then I'm going to have a term which goes like A alpha 2 dagger, A alpha 1 of 0. So obviously this term here is 0 because alpha 1 and alpha 2 by definition have to be different, because else I could not have defined a state like this one. So by definition here, since these are not bosons, alpha 1 has to be different from alpha 2. And we are implementing the Pauli principle for fermions, which for a single particle picture means that we cannot have more than one particle in a given slot. So this means that this term here is automatically 0. And now what you see is that this final term here gives us 0, because now this alpha 1, A alpha 1, which you see here, is acting on the vacuum state. So these two last terms here give us 0. And that means that what we have done now is to shuffle one of the annihilation operators to the right, and that acts on the vacuum state and gives us 0. So if I look at this term here now, so these two terms are 0, both of them, because delta alpha 1 cannot be equal to alpha 2. So these two terms become 0. But later we are going to actually remanipulate this one, because we can rewrite it in we can actually rewrite it so that we have all the annihilation operators to the left, not to the right. So if we look at this first term, we are going to get 0, and then we are going to get a delta alpha 2 minus an A alpha 2 dagger of A alpha 2 acting on 0 times delta alpha 1, alpha 1. And now we have one term here where we have the annihilation operator to the right, so that deletes that state. So this is what we would have expected, delta alpha 2 times delta alpha 1, alpha 1. So we have assumed that these are normalized states. We are setting up a two-body state, which is also normalized. So when we take the norm of these two states, we should actually get just one. So this is basically what we expect to get. Now, if you look at what we did here, we can actually rewrite this operator in this expectation value in a slightly different way. So what I said, if you now look at what we did with this operator here, but also what led to that one, we can introduce a new way, a new notation, which is going to simplify the way we calculate these expectation values, and it's also going to motivate the introduction of Wick's theorem. So one thing which I could have done here is actually to rewrite these terms here so that I have always all the annihilation operators acting on a vacuum state. So let's look at this from the one body type of operators. So we have just one state now. So we are going to introduce a new notation. New notations. And I'm going to introduce something which I will call a contraction. So if you now look at just one such single particle state, so if we look at this operator here, so we have an alpha, and then we have a creation operator acting on the vacuum state. If you look at this, this is obviously when I use the anti-commutation relations, this is now given by my 0 delta alpha beta 0 minus 0 of A beta of alpha, like that. So I'm just using the anti-commutation operators. So what is common then to do is to define something which I call a contraction, which is defined by the Kronecker delta, and something which I'm going to call the normal ordered product of operators. I'm going to define what I mean by that. So if you now look at this expression here, I'm going to write this in a more compact form. So I'm going to have an A alpha, A beta dagger, and this is the same as 0, A alpha, A beta dagger acting on 0, which is the same as a Kronecker alpha. So if my basis, if I write this out, this is given by this one. So I create a state with a particle in the single particle state beta. And then I have on the bra side, I have a single particle state in the state alpha. The basis I've chosen, the computational basis, is orthonormal, which means that I end up calculating this quantity here, and due to orthonormality, this has to be equal to Kronecker delta. So this is going to be a compact notation, which means this. Next thing, which I'm going to do, is actually to just write a plus sign here. And then I'm going to define something. This is not the number operator, but this is a normal ordered product of operators. So when I take a string of operators like this A beta dagger, A alpha, or let's just rewrite it the way we had it. So I have a string of operator which looks like this, A beta. So what does normal ordering mean in this specific case? Normal ordering means that I interchange these two operators so that I have the annihilation operators acting on the vacuum state. So this quantity here is the same as a minus of this expectation value of A beta of A alpha. So normal ordering here means simply that I am moving all the annihilation operators to the right by permuting this. So if you now look at what we have done mathematically, since we use this anti-commutation relation, then mathematically, this normal ordering corresponds to us using the anti-commutation relation for two operators. So the first quantity is just this guy acting on that one. So I can rewrite that in terms of this quantity here plus a normal order product. So in general, this kind of normal ordering, if I take a string of operators, let's look at another example here. This is an example 2. So if I take this normal ordering and I have a set of operators, let's just call this A1, A2, A3, A4 dagger. The way I would now calculate this is simply by putting all the annihilation operators to the right, but then I have to make permutations here, which then follow from the anti-commutation rules. So when I'm calculating an expectation value of this quantity, I'm actually going to have a quantity which now will involve these contractions as well. So this is now given in terms of 1, 2, 3 permutations. So I will actually have minus 1 to the power of 3. And then I'm going to have an A4 dagger. Let me just rewrite this one. So I'm going to have a 0 here, and I will have an A4 dagger, an A1, A2, A3, multiplied with the vacuum state. And this is obviously equal to 0. So a normal order product of operators is always equal to 0. Okay? So if we now go back to this example which we have, the example here, you see now that in order to reach this first term, we have actually normal order, the two operators, we are bringing them close to each other. So you can calculate an expectation value for the two operators. So this is actually the contraction, and this is a normal ordering. Then when we look at this expression here, the next term is actually an equation here, which would then will also contain a contraction plus a normal ordering. But here, when we did the, when we implemented the anti-commutation rule, we got a term here, which ended up in this term. And then we manipulated that one further so that we could have the annihilation operator here. So this is an example of where we've been switching operators so that we have one of these annihilation operators to the right. And then in a certain sense, we could say we could stop here. But what you could do now, if you have these 4 operators, you could actually set this up in terms of a more general expression. So let's look at this example, which we did here, and just run through a case now with 3 such operators, and then we do 4 operators. And we try to rewrite everything in terms of these contractions and normal order products. Because then what we are actually showing with 2, 3, and 4 is Wick's theorem for 2, 3, and 4 operators. And then we are going to use induction to prove it for a general set of operators. And the thing is that with Wick's theorem, we can actually simplify considerably the way we perform these calculations. Because if I'm going to ask you guys to perform all these operations here for 10 particles with a 2-body operator, they're going to hate me. Because that is a meaningless exercise of just playing around with all these anti-commutation rules. And you will just fill in sheets of papers one after the other one. So Wick's theorem, which I wanted to state now, we have actually showed Wick's theorem for 1 creation and 1 annihilation operator. So what you have here is actually Wick's theorem for 2 operators, 1 creation and 1 annihilation. Before we show the theorem, let's just look at this for 2 operators, not 3 operators. So when we have 3 operators, we can either have 2 creation and 1 annihilation operator, or 2 annihilation operators, or 1 creation operator, or 3 annihilation and 3 creation, right? So let's just look at an expectation value, which looks like this. So we have an A1, an A2, and then we have an A3 dagger, right? So this is something which we now can write out. And in all the cases, what we have is that 1 is different from 2, obviously, and this is different from 3. So these are 3 different states, okay? But just restating the obvious thing. So we can now rewrite this one, and then we are going to apply this trick with shifting this creation operator to the left, so that we have only annihilation operators acting on the vacuum state. So the first term here, now if we do this in a brute force way, we would have an A1, and then we have a delta free 2 minus an A free dagger, and A2 of 0. And I'm just going to write this out in terms of the different, all the possible terms which we get by using the anti-commutation rules. So this is obviously equal to 0. And we know now that this term here, this one, is something which we can write out as an A2, A3 dagger, like that, of 0. That's how we defined this quantity, this contraction. Okay. Then, sorry, if I now look at the next term, I have a minus 0, and then I have an A1, and we know that 2 and 3 cannot be equal, so this is obviously equal to 0. It has to be, but let's just keep it like that. So then what we would have is an A1, and then we have the A3 term, A2 acting on 0. And now we can perform a new contraction here. So we get a 0, A1, A2, A3 dagger acting on 0. And then we have this contraction, and then we have a minus. And now I'm having a 0, and then I have a delta. So if I look at this operator, I have a delta 1, 3 minus, and this is multiplied with an A2 here. The 1, 3 multiplied with A2. And then I have a minus, and from the anti-commutation rules. And then I will have an A3 plus an A1, A2 acting on the vacuum state. Okay. Does that sound reasonable when I do that? So if I now look at these calculations, what I will get is the following. So I'm going to get 0, and I have A1, A2 dagger, A3. So these contractions are defined between a creation and annihilation operator. So even if I didn't have this contraction, I would have A1 acting on the vacuum state, which is 0. And then what I have next is a minus, and then I have 0, and then I have A1, A3 dagger contraction, and then I have my A2 of 0. And finally, I have the next one, which is simply, if I now look at that one, which is plus, and then I have 0, A3, A1, and A2 acting on 0. I can now rewrite this in a more general way. So if you look at this one, this is nothing but what we defined as the normal order product of the operators. So this will be the normal order product of the operators A1, A2, A3 dagger. All these terms are equal to 0 because we have an uneven number of annihilation and creation operators. So we are not able to match all creation operators with all annihilation operators. If we now look back at the two first terms, these can be rewritten in the following way. So I have a 0, and then I have A1, A2, A3 dagger acting on 0. And this is going to be equal to 0, A1, A2, A3 dagger of 0, this. And in the first case, we have the contraction between 2 and 3. The next one is something which we are going to write with a plus here, but we have to be a little bit careful because we are interchanging operators. So this is given in this term. That's a contraction between 1 and 3. But keep in mind that this comes with a minus sign here, as you see here, this specific minus sign, because we have interchanged the operators so they can stand by each other's side and then acting on the vacuum state for that specific set of states. And then we have plus of n, the normal order product of these operators, A1, A2, and A3 dagger. And in our case, we end up with a plus sign because we interchange 3 with 2, and we interchange 3 with 1. So we've done 2 interchanges, and each one gives rise to a minus sign. And that follows from the anti-commutation rules. So what you see here is a more compact way of writing this expectation value, or this transition probability here. And that is obviously equal to 0. Now, you could now try with 2 creation operators and 1 annihilation operator, and you would get 0. You can see that quickly. You can try with 3 creation operators, or 3, if you have 3 annihilation operators, this is automatically 0. If you have 3 creation operators, that is also 0 because you are creating 3 particles. So if you have, in this case, if you have 3 creation operators here, that means that when they act on that state, you would get 1, 2, 3, and vacuum expectation value with that one, and that's 0, right? So that means that if you have an uneven set of creation annihilation operators, or only one type of operators, these kind of transition probabilities or expectation values, they always end up being equal to 0. So the thing is that what you see here now is a kind of small hint on how we can rewrite a case with 4 operators. So if we have 4 creation operators, or 4 annihilation operators, or 3 creation and 1 annihilation, we will always get 0. You see that immediately. So we need 2 creation and 2 annihilation operators. This is the only case which will give a non-zero transition probability or norm or expectation value. So after the break, we are going to look at this next case, which is 0. And then we have an A1, A2, A3, and A4. And what you will see is that you're going to be able to generalize this set of contractions to a set of all possible contractions, plus a final normal order product, which simply means that every such set of operators, there will be one term after all the applications of the anti-commutation rules, which will look like this. And that is something you can read off automatically the value of, because it's just 0. So what we are going to do now is to look at how we can perform these operations. And we did already parts of that when we had that norm between a state with alpha 1 and alpha 2. So we've already seen how we should proceed. So it's not much different from that case. But I'm going to rewrite now in terms of all the possible contractions which we can make. So we can now, if we look at this specific operator, one thing is that clearly if we have an odd number of creation and annihilation operators, that is going to be 0, because then we will have an operator which will be left uncontracted. And when we take the vacuum to vacuum expectation value or transition probability, we are going to get 0. So this specific case, if we now look at it, there's going to be one term, which we will just call the normal order product of these operators. And you saw that follows very much this pattern which we did here when we perform all the contractions. So if you go back to that case which we had with the 2-body state here, that means that we would keep manipulating this term here. so that we have this operator and that operator acting to the left, and then the creation of the annihilation operators to the right. And that would give us a term which would just be the final normal ordered part. So we are going to write this as an A1, A2, A3, dagger, A4. Sorry, not that one. Sometimes I'm a little bit too fast with the notations here. And this is automatically 0. Automatically. Then we are going to get all possible contractions between two pairs of operators. So that means that we will get a contraction, and now we write this in a more compact way. So you would typically skip the vacuum states. So we would typically write this as an A1, A2, A3 dagger, A4. And we would have one contraction of this type, which is us just interchanging the two operators using the anti-commutation rules. So we would do that many times in order to bring the operators to a form where we have an annihilation operator acting to the right. And then clearly we would have A1, A2, A3 dagger, A4. And here you can list all the possible contractions, but we know, so let's just quickly remind ourselves, the only one which is different from 0, if I take alpha, beta, this is equal to the Kronecker delta. All the other ones, A alpha, A beta, is equal to A alpha, A beta dagger, and A beta, A alpha, all these are equal to 0. So when we now are listing all these sets of two possible combinations of bringing together one creation and one annihilation operator, we leave out creation to creation or annihilation to annihilation, because they will automatically be equal to 0. So just to see that immediately, if you just take this one, that would be given by 0, A alpha, A beta of 0, and that's automatically 0. So when we now look at the possible set of contractions, we need only to list those which involve one creation and one annihilation operator. So this means that what we would have, and I'm going to write this as a normal order product. So we're going to have a normal order product here. And now I can take this operation. And since this is a normal order product, so we perform one contraction, but then we are left with a normal ordering of A1 and A4. So if you now go back to that example we had before the break, so let's just go back a little bit, you can now see that we get something like this. This is the contraction. And then we have this term, which is a normal order part. But that gives us 0. So there will always be some normal ordering left here. So that means that here, this term here, since I have to normal order A1 and A4, that gives us 0. So all the normal order terms here are going to give us something which is 0. And that is extremely simple. So you can see that if you write out all the possible combinations you can make with the anti-commutation rules. So then we would continue. So we would have N, and in principle, you should list all the possible contractions, but there is no point in taking those which are 0. And the next case would be this one. And the final case here, which gives something which, from the contraction point of view, is non-zero, with the one pair of operators, would be A1, A2, A3, A4, this contraction here. Now, these terms here are all equal to 0. This is equal to 0, this is equal to 0, equal to 0, and equal to 0. Because a term like this one means simply, if I look at this one, what it means is that I'm going to have a Kronecker delta. There's going to be a minus sign because I switch A1 and A2. So I get a minus, and then I have a Kronecker delta of 1 and 3. That is a contraction. And then I have the normal ordering of A2 with A4. So the normal ordering means simply that I interchange the operators so that the annihilation operator is to the right and the creation operator to the left. And this is equal to 0. So if I haven't contracted all the operators, what I get is simply 0. And this would come out from you simply using the anti-commutation rule. So it was actually Wick's kind of streak of genius to realize that most of the terms end up being 0. And then by introducing these contractions and the normal ordering, you could then find a very efficient way of calculating expectation values and transition probabilities. So what you would get then in the next term would be this normal order product of A1, A2, A3, A4, dagger, but where we now contract or perform all possible contractions between these operators. And I'm going to write it like that. So that means that all of them are contracted. So the next one would be A1, A2, A3, A4. And the final one would actually be this one. And this will give us rise to Kronecker deltas. And if 3 is equal to 1, as we did before, alpha 1, and alpha 2, alpha 3, we're just going to get the first term, which is Kronecker delta alpha 1, alpha 2. So this is the way you would set it up. And Wick's theorem, if we now go back to the slides, or we can just state it here, this will be Wick's theorem for 2 pairs of creation operators, or 4 operators in general. So what Wick's theorem says is a general Wick's theorem, which we are going to prove tomorrow. That says that an expectation value of a string of operators. So we have now X, Y, Z, etc., up to some W. So you could think of these as being strings of operators, and each one of these could contain 1, 2, 3, 4 creation annihilation operators. So this is just a string of operators, each one of them. So you can think of each one of these as it could be just one creation operator, or it could be many, or it could be a mix of the creation and annihilation operators, string of annihilation, and creation operators. And this is going to be equal to 1, the normal ordered term for all the operators which are not contracted. So that means we just permute them so that they become normal ordered. That means all the creation operators are going to act to the left and the annihilation operators are to the right. So this is going to be equal to a term here, n, which is just the normal ordering. So that means, as I said, all the annihilation operators to the right and creation to the left. So you could just take, if you have these 4 operators, you just permute them so that you have an ordering of that type. Then there is a sum, and I'm going to write this in a little bit strange way here. So one set of permutations. And that runs over all the possible permutations we can make. So that is a normal order product of X, Y, Z, up to W. And then I'm just going to write it like this. So we're just performing one permutation. This is also automatically equal to 0. And we saw that from the calculation which we had here. So we had one term when we perform all the contractions, which is going to look like this. But then we have one possible contraction, another one here, another one here, and another one here. And all these end up being 0 because we would have a Kronecker delta, and then we have two operators which have to be normal ordered. And that transition probability expectation value gives us always 0. So if we continue like this, you see that there's going to be a pattern here where we now have a sum. Let me just write it. And I'm just going to write a sum over two sets of contractions. And X, Y, Z up to W. And we could write this one like that. So we are contracting, in order for this to be something which is non-zero as a contraction, the only non-zero contraction is one which involves one creation operator and one annihilation operator. All the other possibilities give 0. And this would continue plus till we have all the n-half sets of, so we have n is the number of operators. Maybe we put an m here, m-half. M is the number of operators. So this is n-half because we have to match every creation and annihilation operator. And this is given by the normal product over all possible contractions, X, Y, Z. So this will be contracted with something, this one as well, and then we have W as well here. So that's the final one. So this is a generalization of what we showed for one pair, 3 operators, and 2 pairs, or just 4 operators. So we have 2 operators. We've done the calculations for 2 operators, 3 operators, and 4 operators. When you have an odd number of operators, it's always going to be 0. So you always have to match the number of creation operators with the number of annihilation operators. Yeah.
Was that contractions regarding the strings of operators or the individual operators?
So you would have to break the strings. So when you look at the string of operator, then there's something which is called Wick's generalized theorem. So which is an addition to what we will do now. So now you can think of every X, Y, and Z as just one operator, or you could think of every X, if it's a string of operators, then you have to match them with the relevant operators. But you can, later we are actually going to introduce something which is called Wick's generalized theorem, where you can think of strings of operators. And then generalized theorem says that it's only contractions between the strings of different operators. So you cannot do the contractions between the string itself. So this is an extremely powerful way of doing this. And what I'm going to do now is actually to give you an expression for an operator in second quantization. And then we are going back to how you get this operator. But what we could do, we can take a simpler one, which is the number operator we looked at last week. So let's look at the number operator. And this is now acting on 2 states. So on a 2-particle state. So the number operator is given by this sum over all the possible states which the system can be in. And we are going to look at a expectation value between a state where we have filled in 2 slots. So this is a single particle state. So this is a sum over alpha. And then we have an A alpha dagger, A alpha. And then we have a state alpha 1, alpha 2. And this is what we did last week, actually. So the kind of operators which we are going to look at now is going to be given by the following. So if we take just this term here for one specific alpha, what we will have then is the following. So we have 0, and then we have an A alpha 2, A alpha 1, and then I have an A alpha dagger, A alpha 1 dagger, A alpha 2 dagger. So if I look at the normal order term, which would actually be this term which you see here, this is automatically 0. Then, if I now just look at one possible contraction, like this one or that one, I can do this one, etc. That will always give me 0 because I'm normal ordering the 4 other operators. So the only possibility here is actually the following, because now I'm fixing alpha, so I can have the following contraction. So I have A alpha 2, A alpha 1, A alpha dagger, A alpha 1, A alpha 2 here. So I can have this contraction, but that obviously locks my alpha to be equal to alpha 1, right? Because if alpha is equal to alpha 1, it cannot be equal to alpha 2. So that means that the only other possibility here is that one. And then we have this guy here, okay? Because alpha, due to the Kronecker deltas, this gives me delta alpha 1. So, and this is an expectation value now, which simply gives us that we have delta alpha 1, and then obviously have alpha 2 equal to alpha 2, which is obvious. So I'm just gonna set up the Kronecker delta of alpha 1. Then you see immediately that the other contraction, which we can have, is now alpha going to alpha 2 here, and then clearly this one going like that. But now we have to be a little bit careful, because when we are performing these operations, then the operators have to stay together in order to calculate the expectation value. So what we would need then would be to interchange alpha 1 with alpha 2. That gives a minus sign due to the anti-commutation rule. But then I would also interchange these two, and that gives me another minus sign. So then I have minus minus, so it gives me plus. And this is equal to delta alpha 2. So if I then go back to the summation here, that sums to 2. So this counts the number of particles we have in a state. Okay? So you go back to the summation here, and then you see that this gives us a number of particles. So this is much better than what we started with last week, when we tried to manipulate it so that we got by the anti-commutation rules. This is a brute force way of doing it. You can do that with a 2-particle state and a 1-body, perhaps a 2-body operator, but it doesn't get that exciting if you do it with a many-particle state. And then that is why Wick's theorem becomes much more compact, and it allows us to set up just all the possible contractions. Later, however, we are going to introduce something which is widely used in condensed matter physics, in quantum chemistry, nuclear physics, etc., which is called the particle hole formalism. So we're going to define states above and below the Fermi level. And that is going to give us a redefinition of the vacuum state in terms of all states filling up single particle slots up to the Fermi level. So we are going to redefine the vacuum state, and that is going to give us a more compact formalism, which, because if we have 100 particles, even with Wick's theorem, you wouldn't like to do all the contractions involving 100 particles. So we are going to do a further redefinition. You can always redefine your reference state, whether that is just plain emptiness or it is a specific reference state, which could then be the ground state ansatz for a given system. So in solid state physics, where you often have a gap, so like in semiconductor physics, you have the so-called band gap, which is something probably many of you have met. And that often defines a set of states which are occupied up to a certain energy level. And then you have excited states above that. And that allows for the introduction of a more compact redefinition of the vacuum state. And the same is used in quantum chemistry, where you would use a closed shell atom, like the atomic neon, as one reference state, and then you can look at excitations around the Fermi level. So that would imply a slight redefinition of the vacuum state, which we are going to discuss next week. But Wick's theorem now allows us to make the calculations in a much, much easier way. And you see now that compared to what we started with in the beginning of the semester, when we calculated an expectation value of a Hamiltonian in the standard so-called first quantization approach, this is a much more compact way of calculating these expectation values. So the next step, which we're going to look at, is another operator. And what I'm going to say now, and then I'm going to show it later, you will find that in the lecture notes, is that the representation of this operator in second quantization or in the number representation is something which we can rewrite as a sum over two states, alpha and beta. And then we have a transition probability, or if these are eigenstates, if this is beta and alpha are eigenstates of H0, this just becomes equal to a single sum. But let's just assume that it looks like that. And this is going to be given by a creation operator and an annihilation operator. So this is the so-called one-body operator. It doesn't need to be kinetic energy and single particle potential energy. It could be an operator for some transition probabilities. So it could be the action of an electromagnetic field on a single electron, for instance, where you then have a transition probability from a state alpha to a state beta. And we generally call this just for a one-body operator. So let's now assume that this is the single particle one-body operator of the Hamiltonian. And we have, earlier we have said that when we act on this state, this should be equal to an epsilon beta times B. So we can assume that this basis is an eigenbasis. And if that is the case, life becomes much simpler because we have also Kronecker delta between the basis sets. So we have a delta alpha beta. And then the operator reduces simply to a single sum. So I would have an epsilon alpha multiplied with A dagger alpha, A alpha. It doesn't need to be that simple. It's not guaranteed that we have a one-body basis here, which is an orthogonal base or orthonormal basis and an eigenbasis of H0. But that's a pretty common choice. But if you have another type of operator, you would have a basis, a computational basis, and then you would have to calculate those transition probabilities. Now you see that if you go back to the number operator, the only difference between the number operator and this one, in the number operator we had A alpha dagger, A alpha. So the only difference is a constant. But if you now look at the expectation values which we are getting, so if we now look at this specific state, which we looked at, of H0, of alpha 1, alpha 2, what we end up with then is the following. So if we just write down the same expectation values we had before, if we do that, what we would have is a sum of alpha. We have this epsilon alpha. And then we just need to look at A alpha 2, A alpha 1. And then we have A alpha 1 dagger, A alpha 2 dagger of 0. And here we use Wick's theorem again. This term, which you see here now, this term, is exactly the same as we had for the number operator. Which means that when we now perform the contractions, this is simply going to be given by alpha, epsilon alpha, which is going to be multiplied with a Kronecker delta with alpha 1, plus a delta alpha 2 here. And then we have simply epsilon alpha 1 plus epsilon alpha 2, which is what we got when we calculate everything by setting up a 2-particle Slater determinant. And then we ended up with the sum of single particle energies. If this is not an orthonormal basis, then obviously we have to calculate that integral, and then we would have to perform the sum over alpha and beta. But it's not that more complicated than what we did here. So here we could just reuse everything which you did with the normal order, no, the number operator, sorry. Okay, so the thing we need to look at now is where did this magic expression come from, which seemingly makes life so much simpler. So in order to see how we can derive this one from what we had before, because before we had an operator which contained a second derivative, which is a kinetic energy, and there could be a potential energy term. So how can we translate that one into an expression which looks like this? So in order to do that, let me quickly remind you of something which is called the spectral decomposition of an operator. Have you encountered that in courses in quantum mechanics? Yeah, doesn't ring fully a bell. So let's just quickly remind ourselves about this technicality. Spectral decomposition. This is also something which becomes very handy in more kind of modern quantum mechanical descriptions. So what we could do now is to define, this is general what I'm setting up now. So you can define an orthonormal basis, ONB. This is a kind of acronym we use for the orthonormal basis in some kind of Hilbert space. So this defines our Hilbert space. And this basis, I, contains now just a set of states which are orthonormal to each other, or 1, and this goes all the way up to some state n-1. So you could think of that as a many-body or single particle Hilbert space. And this simply defines our space. In principle, this little n is infinity, right? But we are assuming that we have a finite Hilbert space, so we can run calculations in that. But normally we always assume that, but then we make truncations. So that means that I am also going to assume now that there is an operator, which I'm going to call for A. So we assume that there is an operator A here as this I as an eigenbasis. Now, what I can do then is obviously to expand a new state in this orthonormal basis. So I'm setting up a state psi here, which is simply now the summation from I equals 0 up to n-1. And then I have some overlap coefficient multiplied with I here. So alpha y is just an overlap coefficient between that state and the orthonormal basis I've chosen. That obviously means that when I act on A with psi, there's also another assumption here is obviously that the norm of that state I equals 0 to n minus 1. The norm of that one is given by alpha I squared. And we want that one to be 1. That's for the state psi, okay? Then, if I act on that one, what we have is I equals 0 to n minus 1. And then I have my alpha of I, and then I have A acting on I here. And that is the same as an eigenvalue, lambda y of I. Then it's pretty common to define a projection operator. So we would then define a projection operator in terms of that orthonormal basis, which is just called PJ, which is the outer product of two of these orthonormal states. Remember when we just had the case with two states, 1, 0, 0, 1, we could then form a projection operator, which then just projected out one of the states. So, and we also know that this PJ squared is equal to PJ. So if I act with this PJ on that state psi, what I get then is obviously J times J. And this is then acting on this sum from I equals 0 to n minus 1 of alpha y of I. And that is just the sum I equals 0, n minus 1. And then I would have this overlap coefficient alpha y. And then I would have a J. And then I have J of I. And we know that this is an orthonormal basis. So what this is actually doing is that's actually projecting out a specific component of that vector psi, which is a linear combination of all the orthonormal basis states. So if I then act with an operator, this operator here, on that state, if we now look at that one, just remind ourselves of that. That is equal to I equals 0, n minus 1, and then an alpha y of lambda y of I. We see now that this term, which we have here, could now be recognized as the action of this projection operator. So what I could do now is simply to rewrite this in terms of I equals 0 to n minus 1 of lambda y, and then I have a P of I. So I'm going to put a hat here, P of I acting on the state psi, like that. Because my operator, the action of that operator, P of I of psi, gives me this term which we see here. And that means that what I can do then, if I look at this expression, is then to define the spectral decomposition, or the spectral decomposition of that operator in terms of I, from 0 to n minus 1, and then I have my lambda y multiplied with P of I. That's the spectral decomposition of an operator. Where this lambda y then is one of these eigenvalues of that operator A. So this is something which you probably have seen. It's if you take a normal course in quantum mechanics, some of the first ones, it's not often used, but it is much more used in connection with the introduction of what's called the density matrix. And also if you do quantum computations or quantum computing, this will be an expression which comes up again and again. Now, in the development of that expression for the operator, we actually need the spectral decomposition. So the material which I'm going to present now, and I see we are running a little bit out of time. If we just go back to the slides here for this week. So let's take a look at that. And these should be somewhere. I think I have it somewhere here. Now let's just stop it and then. Okay, just go to full screen and then share again here. Yeah, you just. So if you go to the weekly slides, which we have for this week, and what we would start with then is actually this representation in the standard first quantization approach. So this would correspond to the application of the spectral decomposition. And what we do then is that we use this way of rewriting the operator, and then we let it act on a set of product states which come from the Slater determinant. And the first case is without a permutation. And then you remember that the next case, we can interchange particle 1 and 2. And then we can interchange all the other one. We can look at all the possible permutations which are available. And by doing that, and this is something which we will pick up tomorrow, I won't write down all these equations because it's actually a boring thing to do. It's just a manipulation of indices. So I invite you to just take a look at these expressions here, because when you've gone through all these permutations, rewritten the sums, a very exciting thing, then you end up with the type of expression which we applied in the previous implementation. And then you can repeat this for a two-body operator. So which means that for the two-body operator, and this has an example, which for the two-body operator, you would simply rewrite this in terms of a spectral decomposition where you act with on a two-body state. And then you can take the full Slater determinants and perform all the manipulations. And when you've gone through that, you end up with the final expression for the operator, for the two-body operator, which looks like the one which you have here. So what I normally do, simply because it's a boring exercise of interchanging indices again and again, is that I ask you guys take a look at it and see if you're convinced. And then tomorrow, we're actually going to use these equations and we are going to derive or prove Wick's theorem, which gives us a compact way by which we can calculate these expectation values. And in the examples you see in the lecture notes, I've actually done all the contractions. And this is okay to do with two particles, but you wouldn't like it so much if you were to do that with more and more by just looking at all the possible contractions. So take a look at this brute force way of doing it. And then tomorrow we are going to wrap up the discussions with the proof of Wick's theorem. And that will be the theorem which we will apply to the calculation of expectation values, which gives us a much more compact formalism, because the thing we are going to pick up, because you see when we perform all these contractions, we never think of the actual integrals. So the actual integrals would be something which you pick up at the end. So this would be something which we have tabulated, or something which you can calculate quickly on the fly. So take a look at these derivations for tomorrow. So I'm just giving you a kind of mini homework. And then we will focus more on the applications and the derivation of Wick's theorem. So I actually, once I went through all these derivations, and I think I put people asleep actually. So I don't want to do that again.